Hello, thank you for joining us today. My name is Jessica Ramirez, and with Charlie Shales and Meng Shang, we're going to discuss the project that we work on in the Civic Data and Technology Clinic. But before jumping in the presentation, we want to thank the University of Chicago, the 11-hour project, and Hokonu for supporting us throughout this quarter. So what is Hokonu? Hokonu was founded to address this limited access to oceanography data, mainly because the instruments that measure water level tend to be highly expensive. So Hokonu was launched to democratize access to remote ocean observing technology by offering low-cost and solar-powered internet-connected hardware that captures data at a comparable accuracy to industry standard tools that cost over $100,000. And so, with water level prediction, they assist communities harmed by frequent flooding. And why coastal monitoring is important. With water level data and statistical tools, one could predict potential floods. And this enables efficient data driven responses and proactive planning for coastal floodings. Additionally, this data can be useful for organizations that own property in flood prone areas to quantify risk. Also, in this context of climate change, where floods have become more frequent, there is a increasing demand of coastal monitoring. And finally, access to oceanography data allows for integration of community and technology to further study the ocean. Now, about the project impact. Before the implementation of the pipeline that we developed, Hokonu faced two main issues related to its data. First is that local water data needed to be standardized to common measures used among the oceanography community. Second, the low cost in hardware also limited the data quality. So, with the pipeline implementation, we were able to calibrate the data to standard measures, increase the data quality with a specific anomaly detection test, and also increase the accuracy in water level predictions by adding some external data. So overall, with the pipeline, now Hokonu can deploy a node anywhere with reliable data. Before developing the data pipeline, we needed to gather some additional external data, given that Hokonu stations do not span over a 19-year period, which is needed to make the data calibration. So we scrape water level data from the National Oceanic and Atmospheric Administration, who runs highly sophisticated coastal monitoring stations across the US. For example, in this map of South Carolina, NOAA has 3 stations. We can deploy many more Hokonu stations at a lower cost and get advantage of this NOAA network to enrich the data. Now we're going to explain how the data pipeline works. First, we have these objectives of data retrieval, calibration of the data, improved data quality, and then the water level prediction. First, we fetch the requested Hokonu's water level data, and we get the nearest NOAA station from that Hokonu node. We get the water level data. And once we have that, we can move to the data calibration part. So for both of the nodes, Hokonu and NOAA, we get the datum information. In the next slides, we will explain what are datums. And once we have that information, we can make the data calibration. However, most of the Hokonu nodes don't have datum information. So we use NOAA and the TAD algorithm to estimate those datums. And then we can convert Hokonu data to standard water level measurements. After that, we clean the data. So the data goes through some anomaly test called the quartet test. And once some of the anomalies are flagged as missing or fail, those are imputed. And finally, we make the water level prediction with 3 months of data. And now Charlie will explain what are the datums.
Now we'll talk about data calibration, specifically how we calibrate the raw Hokonu sensor data to be on the same scale as the data from NOAA stations. This involves working with and estimating tidal datums, so let's all be oceanographers for a minute and talk about tidal datums. Tidal datums are standard elevations defined by certain phases of the tide, which for the government-operated NOAA stations are calculated over a 19-year period. We're particularly interested in the lowest tidal datum, the MLLW, or mean lower low water, since a station's water level is often reported relative to its mean lower low water datum. Hokonu sensors measure the distance from themselves to the water below. To get this data to be invariant of the height of the sensors and on a scale oceanographers can use, we want to convert the Hokonu sensor's raw data, in the diagram, the upside down D2W or distance to water data, to the NOAA standard, right side up and relative to mean lower low water, but without needing 19 years worth of data. So to do this, we will use the TAD algorithm. The TAD algorithm, which stands for the Tidal Analysis and Datums Calculator, is a calculation developed by NOAA that computes tidal datums. We will use this to convert the Hokonu sensor's data to be on the same scale as the data from NOAA stations. So in the diagram, we multiply the Hokonu's distance to water series by -1, as shown in the first graph, to change the measurements to right side up. And then we use the TAD algorithm to figure out how to shift up that series to the level of the NOAA station that is closest to the Hokonu station, as shown in the second graph. In the TAD algorithm, we don't just calculate a simple average difference between the Hokonu data and the nearest NOAA station data. We calculate the average difference at the high tides and at the low tides. The raw sensors data can have high frequency movements, shown in the left graph, that make it more difficult to identify when the high tides and low tides are occurring. We use a low-pass Butterworth filter, shown in the middle graph, to smooth out the raw sensor data and easily identify the high and low tides. The filtered signal is used to identify the times at which there are high peaks and low peaks. The observed unfiltered data points closest to these times are then recorded as the high or low tides, as shown in the right graph. This process is repeated for the nearest NOAA station. So now that we've identified the high tides and the low tides for the Hokonu series and the nearest NOAA series, as shown in the left graph, we compute the average difference between the Hokonu station's high tides and nearest NOAA station's high tides, and similarly for the two stations' low tides. As you see in the right graph, we use this calculated average difference to shift the Hokonu series up to the level of the nearest NOAA station. Now the Hokonu data is relative to mean lower low water, which is the NOAA standard. Next, Mengchen will talk about the quartile tests and the VAR model.
So right now we have better data collaboration here. We are able to conduct anomaly detection not only on the global scale, but we can zoom into the local scale, which is a point-by-point scale. We can examine each point to be correct and reasonable. And the previous job did not do well because they didn't incorporate the nearest NOAA stations data. So we are able to solve this issue and created several new detection functions to be more accurate. And the first one is a gross range test. We can see on node 69, the gross range should be within this area and the quantiles should be within this area. And our function is able to detect this outlier here. The next test is called flat line test, which is quite straightforward. We can see this part of data form into a flat line here, which means they did not move for several time intervals, which is not normal, and our algorithm detected them. The next test is called spike test. We can see in this curve there are several fluctuations on each point, but only 6 of them meet the criterion of a spike. So instead of eyeballing through all the curve, our function can easily capture the real spikes. And the next test is called rate of change test. So we wanted to make sure within a time interval, the rate of change is not too extreme, which is not normal. We can see these two observations here. The change is too abrupt, so our algorithm is able to spot them. The next test is the neighborhood test, and we can incorporate the nearest NOAA stations data, which is the blue line, and we compare the trend with the red line, i.e. Hokonu stations data. We can see these two observations. They have different trend, which is not normal. So our algorithm again detected them and flagged them. After flagging all those abnormal and missing data, we are able to impute them. And after being imputed, we can use the data to conduct water level prediction. In the previous job, we were using an auto-regression model, which is an univariate model. So we could only input either Hokonu stations data or nearest NOAA station data to do prediction. However, right now with our pipeline, we are able to use vector auto-regression model, which is VAR model. and it is a multivariate version of the previous model. So we can input both Hokonu stations data and nearness NOAA stations data, which improves the accuracy and decrease the variance a lot. So what we do on our bar model is that we use 1 month window to train the model, and we slide over 1 day for each model. So we have many models right now, and we calculate the root mean square error of prediction to see their performance. So on Note 69, we can see the performance looks like this. The previous model, an AR model, they are more biased and more variant. And with a new model, the prediction accuracy really improves. And also, different models' root mean square error also are close to each other. So right now, the new prediction is less biased and less variant. We can see on different type of tide, Note 46, and performance is also very satisfactory. We decrease the bias, and we also decrease the variance. And the prediction is very accurate. We only have 0.08 root mean square error on both Hokonu and NOAA stations. And we test this algorithm on even more fluctuating node, which is node 33. And we can see the performance is also very stable. And the accuracy is also still less than 0.1 root mean square error. So we can see the improvement of the prediction. Finally, I would like to wrap up with the accomplishments we have for this project. So let's jump back to our pipeline. Right now, we have better data collaboration and interpretability, which means Hokonu stations data right now is usable and comparable because we have the same datums right now, and we are able to convert them. And for data quality, we are able to incorporate the nearness NOAA stations data, which increase the reliability, but also maintain the low cost of our data. And as for water level prediction, as we saw in previous several slides, the performance of the model improves a lot based on our pipeline, and we can generate more accurate and less biased, less variant outcomes. So Hokonu's organization is able to deploy node anywhere, and with the algorithm we have right now, we can maintain the budget to be very low, but data to be very reliable. So finally, I would like to represent the whole team to thank 11th our project organization. With your help, we are able to finish this project. And we'd like to thank Hokonu's station and organization as well, because you provide us really precious data and resources. Also, we have really, really great instructors. We have Professor Uniski and our data scientist, Daniel, and technical support, Lona. With all of your guidance and support, we are able to finish this project timely and successfully. So thank you.